We have a few more convergence tests to talk about today. We will also have one more topic on the radius and interval of convergence on Monday. And then, oh yeah, Tuesday I forgot. So Tuesday
I'm coming.
not worry about. Wednesday is finding an error bound. How many things are going to kind of time out poorly? So Thursday, Friday we'd be reviewing, and we'd test the Monday after on Chapter 10.
What are we gonna do? What are we gonna do on
Tuesday, probably just some review on the stuff we've already done for Chapter 10. Maybe look at some of the AP questions, like the free response AP questions you'd see on them. And then after that, we'll have Chapter 11. Chapter 11 is only 3 sections, but I'm going to pull from some outside resources, so it'll take longer than just 3 days. They're shorter than they should be. So we're going to be finding convergence or divergence using a few more tests. What tests do we already know?
Ratio test. Like,
Ratio?
Yeah, wait, is that right? Comparison
test.
I don't know why I always think it's
And
called.
term tests, okay? So we know 3 tests already. We also have a type of function we should just be able to recognize and say, or a type of series, we should be able to recognize and say, hey, I know that converges. Geometric series. We know series of that form converge automatically just by looking at it. So our first test today is called the integral test. Again, this test only works if a sub n has positive terms. Which has been a requirement for most of our tests. If a sub n equals f of x, if I treat my series, or my sequence, series is the adding part, sequence is what you're adding. If I treat that as a function, then the series, and they say n equals capital N to just say, it doesn't have to start at 1, doesn't have to start at 0, just can start at an integer of some sort, a sub n, and the integral starting at that same integer to infinity of the function both converge or diverge. So now we kind of see the purpose of Chapter 9. Those improper integrals are very useful for this test because we're going to have to integrate some improper integrals. When we integrated improper integrals, what did we have to change about this before we could integrate? Infinity had to be replaced with b, limit as b approaches infinity. So let's look at this example. Does this series converge or does this series diverge? Like how you guys were trying to be so quiet with that. So thinking in general, what if I'm just given a random one and we don't know, hey, let's use the integral test. I was like, well, what if I didn't know this was an integral test problem? What happens if I go use ratio? So I tried it. I went and used the ratio test. You don't have to write this down, but just to show you. Again, I'm going to rewrite that as to the 3 halves, so we'd have n plus 1 to the 3 halves times, we flip, so n to the 3 halves over 1. I could combine these to be all under 1, and there's the limit out front, but since we're not writing this down, I'm being super lazy. And then, what was our trick with something like this?
Then that is R.
Okay. That would be R if we were raising to the n, but we're not raising to the n. What was our trick with the inside?
Multiply by 1 over 1.
Multiply by
A clever form of 1.
Clever
which is
form of
1
one.
over n over 1 over n, which is just 1 over n, which is 1. So then your n cancels, your other n cancels, you get 1 plus 1 over n, which is 0.
Okay, what would this limit be as we go to infinity? 1. So this whole limit would be 1. Why is that a problem with the ratio tests?
Doesn't prove anything.
It doesn't prove anything.
Right? What?
I also tried the nth term test, and I also got the doesn't prove anything. So I tried some of the other tests, it didn't work. So now I'm going to try the integral test. So the integral test says we just integrate this inside stuff as if it were a function instead of a sequence. A sequence is discontinuous. We call that discrete, where a sequence gets a point at 1, a point at 2, a point at 3, but we don't connect those points. We call that discrete instead of continuous. So I'm going to be integrating this. Now we go through and integrate like we would normally. We have to replace infinity with b. So we have limit as b approaches infinity. Integral from 1 to b. How can I rewrite this so I can actually integrate this?
Bring n
N to the 3 halves, so n to the negative 3 halves. Oh, I should have written x dx or n dn, not n dx. Just a small detail that. Come on. Fine. I guess we're leaving it n dx.
Oh.
Okay. So now we can actually integrate. The integration of this isn't too hard. What is the integral going to be? What's our integral? Eliana, what's our integral?
2 over 3. No, negative 2 over 3.
What do we have to do before we put that out front? Add 1 first. When we differentiate, we put it out front, then minus 1. When we integrate, we add 1, then put it out front. Oh, okay. Yeah, no. So this part. So now, yeah.
Negative 2.
Evaluating from 1 to b. So now we can do our fundamental theorem of calculus. Equals limit as b approaches infinity. At the same time, I'm going to rewrite this underneath, so we'd have negative 2 over b to the 1 half plus 2 over 1 to the 1 half, because we had minus minus, which makes plus. And now I can do my limit. If I plug in infinity, what's going to happen?
You're gonna get
0 plus
2.
So when our integral was a number, what did that mean about our integral? Whether, because we're trying to ultimately decide if it converges or diverges. So if our integral equals a number, Ben said, well, it converges. So if our integral converges, what does that mean about our series? it also converges. That's the point of the integral test. If the integral converges, so does the series. What if my integral had diverged? What if I go through and I get infinity? Then the series also diverges.
So this proves both.
So the integral, keep doing n dx, converges. Thus, the sequence series converges. If one converges, so does the other. If one diverges, so does the other. To converge or not to converge?
That is the question.
Whether 'tis nobler in the mind, suffer the slings and arrows of outrageous fortune, that's all I know.
Have you seen the
Oh, I
Sesame
thought you were
Street?
going to keep going. I was like, okay, well, that's
Have you seen the Sesame Street version of that? It's pretty sick. YouTube it.
even more smart.
Okay, does everyone have this down before I go to the next page?
I forgot what
Nope.
it's called, like theater. I was gonna be like smart. I'm a theater mom.
I had to memorize it for middle school theater class, and that's why I remembered the next line. But then I can't remember anything
I
after it.
remember that one. Oh my gosh. I was so nervous.
So we're ready? Okay. I want you guys to try this problem. So when we went through solve this, what do we find out about this function? Goes to infinity, so it diverges. Now, there is actually a pattern for this. Series of this form follow a general rule. Let's think about what we did so far. We did 1 over n to the 3/2, and it converged. We did 1 over n to the 1/2, and it diverged. What's the difference between those two? When I brought these up, n to the negative 3/2, n to the negative 1/2, what's going to happen when we integrate? What happens to each of these when we add 1 to the exponents? Okay. This one would be positive 1/2 when we integrate. What's going to happen to this one? Negative 1/2. So if I can still get a negative exponent when I integrate, we're going to converge. If I end up with a positive exponent when I integrate, I'm going to diverge.
Divergers.
They're the divergers.
It is a book.
Divergers is
No, divergent.
Divergent and then divergent mixed together. Good job.
Okay. So a series of this form is called a p-series. This is another one like a geometric series where we're hopefully going to get to the point where we can look at it and say, hey, that's a p-series. I can know automatically whether this converges or diverges. So the rule is we converge if p is bigger than 1. And we diverge if p is less than or equal to 1. So again, hopefully we'll come to the point where we can just look at a function like this and say, p-series, I know if it converges or diverges, just like we should be able to look at a geometric series, and they're kind of backwards. This is a number to an exponent of n. This one is n to a number exponent. So I kind of keep in mind how they relate to each other to help me remember. And then one of these p-series has its own special name, and that is the harmonic series. when P is 1.
Harmonic.
If we just have 1 over n, that's called the harmonic series. It has its own special name because it's really hard to tell if it diverges or not. Okay. It does diverge, and that was in our, if P was 1, we're in the diverge column. So it diverges, but it barely diverges. It goes to infinity so slowly. Like, if we have e to the x, that gets to infinity pretty quick. This will get to infinity, but it's about the slowest moving function that will get to infinity out of all of them, which is why it has its own special name. It will get to infinity. It's just gonna take its time doing it. It is
How do
the
you
turtle.
Get to infinity.
True. If the example they had in the book is they said, how many terms would you need for this number to get over 20? Like even just to reach bigger than 20? I don't remember how much it said. I was just looking at the...
What?
So, to get, for this to add up to be over 20, just over the value of 20, it takes 178,482,301 terms for this to add to something bigger than 20.
Oh.
So, almost 200 million terms just for this to get bigger than 20. Whereas if we have e to the x, how many terms does it take for that to get bigger than 20? Like 3 or 4, you know. This one takes 200 million terms to get bigger than 20. It's just very slow moving.
Can you imagine time? Can you imagine respect to that? Like time and respect to it.
Okay, so we've talked about our integral test. So now we have nth term, direct comparison, ratio, integral. Now we're going to have limit comparison test, which is similar to the direct comparison test. Again, we need to assume our series is positive terms. So suppose this time, since we've got to compare it to stuff, we need 2 series. Suppose the sequence a sub n is bigger than 0 and b sub n is also bigger than 0. The limit comparison test really looks almost exactly like what we did when we were comparing how fast the growth rate of a function was when we had to compare, well, is e to the x faster or x squared faster? And we went and put limit as n approaches infinity of e to the x over x squared. Saw what we got. That would give us infinity. We said, well, the top function grows faster then. So it's very similar to that. We have to do the same idea. We have to divide our functions. So if this were to equal a constant, when we were comparing functions to see how fast they grew, and they equaled a constant, what did that mean about the 2 functions? Do they grow, does one grow faster, does the top grow faster, bottom grow faster, or they grew at the same rate? Okay. This one grows at the same rate, which means if they grow at the same rate, they both converge or both diverge, kind of like our integral test. So if they specify c is between 0 and infinity, then the series a sub n and the series b sub n both converge what if we equal 0? Well, if they equal 0 and B sub n converges, then A sub n converges, so again, if B sub n diverged and we equal 0, then that gives me no information at all. As far as limit came out as 0 and B sub n diverged, we don't know anything. The last one is if we equal infinity. And B sub n, sorry. Thank you. Kind of, sort of infinity. Or crazy looking eyeballs. One of the two.
That reminds me of the alien smiley face.
This little Linda thinks I'm funny.
Maybe we're internally laughing.
Okay, so if we equal infinity and B sub n diverges, then A sub n diverges.
Have you never been in the tunnels? I've been in the tunnels. It's creepy. It's like the tunnels at BYU. Gross and it was awesome, but like it's gross sometimes
Where'd you get it?
from underneath the stage.
Did you go far enough to find the classroom that's just off there? There's a little chemistry classroom just off over there.
There's a chemistry classroom. We didn't go that way.
Yeah, I went in and there was like this paper closet, and the only flashlight we had was my lighter, so it was kind of sketchy. So we went in, we found this chemistry classroom.
I've never been in the tunnels, so I have no
Yeah,
idea.
it was under there.
We should go.
Last time I went, it was locked. I don't know if
You
it's
realize
locked, so-
I don't have a key to the tunnels, right?
You can go ask for one. Like, can I have a key to the tunnels?
I really want to go explore.
Amber told me one time we're gonna go exploring in the tunnels.
Oh, yeah.
She's like,
Okay.
never goes.
It's fun.
We'll set a class. Okay.
So, do you guys have the example written down already? Okay, write the example down. Instructions are still, does this converge or diverge? Now, why wouldn't I want to use the integral test on this one? That would not be pretty to integrate. It looks kind of hard to integrate. So integral test is probably out. Ratio test might work, but it's also going to be hard to simplify. Ratio test seems really best if you have factorials or if you have exponents involved. Those cancel out nicely with the ratio test. This one, we've still got to pick a function, so I need to pick my function. What was our way to pick a function when we did direct comparison tests?
Find one that's bigger.
Find one that's bigger, but how did we usually find one that was bigger?
Get rid of like simplify.
Get rid of the plus ones. Okay. So I'm going to pick 2n over n plus 1, or sorry, not n plus 1 squared, over n squared. So why can't I use direct comparison test if I just picked one by simplifying? Do I have any guarantee that that function is bigger than the other function?
No.
When we did direct comparison, we always just had to get rid of
The bottom.
the bottom one, which guaranteed us we were bigger. This one, there's no guarantee that we're bigger. But we pick it in a similar fashion. We get rid of the plus values. Now, I can simplify that. How will that simplify?
2 divided by n.
2 divided by n. So, let's think back to something we've learned today. What kind of series is that? It is? I think you were picking at random, but yes, that is the harmonic series. It has a constant out front, but it's still harmonic. So, if this is the harmonic series, what are we expecting that series to do? This diverges. So, we're hoping for case 1 or case 3 to happen. We either want our limit to come out as a constant because then both things diverge, or case 3, infinity, so that a sub n would also diverge. So we need to do our limit now. As n approaches infinity of 2n plus 1 over n plus 1 squared divided by 2 over n. This I'm considering a sub n. This I'm considering b sub n. And I want it in the denominator on purpose because then we could take case 3 could be possible. So usually we put the one we pick on the bottom. So now, what do we know for dividing two sets of fractions? Multiply by the reciprocal. Now I can distribute that n in the top, in the numerator, to the 2n plus 1. We have limit as n approaches infinity, 2n squared plus 1n over 2 times n plus 1 squared. How am I going to find the limit of something like that? How do I find the limit as n approaches infinity of that? Okay, possibly. What do we have to check before?
Infinity over infinity.
Okay. So what happens if we plug in infinity? Okay. Or it could have been 0 over 0. That also works with L'Hopital's rule. So I can apply L'Hopital's rule. We have infinity over infinity. We're good to go for L'Hopital's rule. So L'Hopital's rule, we'd have limit as n approaches infinity of 4n plus 1. And then in the denominator, we're going to have to do a chain rule. Derivative of the outside. 2 times 2 makes 4. N plus 1 to the first times 1. So,
Wow.
what happens if we plug in infinity now?
It's primitive. Oh wait.
It will on the next one.
Do it again.
Yeah.
Okay, if we plug in infinity now, we get infinity over infinity
Yeah,
again.
but I was just getting ahead of myself.
Yeah, you're skipping to the next step already. We get 4 over 4, which is 1. So what case does this fall under?
1.
Case 1, they act the same because we equaled a constant. They act the same. So we did have to check that the function we picked either converges or diverges, which we checked originally by recognizing, hey, this is a harmonic series. So, since the function we picked diverges, so does the original. We diverge. So I have one for you guys to try. And then I think we're going to have to skip the last test today and move it to next time. Christmas miracle. We're on a different page.
Christmas miracle.